Myself Srini, and I got Christoph and Alexi with me to talk about Qualcomm audio, both hardware and software side of things with respect to Linux. I think this is the first time we are really talking about Qualcomm audio in a public forum. Most of the information for this presentation is publicly available, so you can take a look at it. So what we'll cover today is just basic talk about the IP block in general. Where is it fitting in complete Qualcomm hardware SoC, and we will probably go through typical audio use cases which we have encountered so far on laptops, IoT platforms, or any other mobile platforms. And the Qualcomm audio has different configurations, so we'll also see how things fit in a different product line. For example, Chrome has different setup, and normal mobiles have different setup, things like that. So that's one thing, and then we'll cover about the audio on Qualcomm hardware is mostly driven by the DSP. So that means DSP has audio architecture. So what are the different types of it, and then and we'll go deep dive into each of them. I guess that's and finally, at the end, we'll discuss about what are the next upcoming features. Okay, so let's start. So this is derived from one of the links I shared there. It's a public documentation, and the Qualcomm audio hardware is called LPAS. It's low power audio subsystem, and that itself contains an audio DSP and lots of audio interfaces. So like I2S, Soundwire, Bluetooth, Slimbus, and PCM, TDM. So most of the time, the DSP programs those interfaces, but in some use cases, for example, Chrome, we program the interfaces directly. The audio LPAS audio system also has many blocks actually, not just one block. So this is one of the example wherein you have a Soundwire interface which is connecting to a smart speaker for the mobile phones, and we also have an external codec which is supporting a Soundwire interface. It could be WCD or any other standard Soundwire interface codec, where you provide the analog functionality like headsets and mics and DACs and things like that. So this is the typical layout of the blocks. Right. So as I said, the hardware itself contains a core, a DMA, clocks, and interfaces, and there's some digital part of the codec inside the hardware, inside the LPAS block as well. That's what we call LPAS codec, WSA, VA, TX, and all that stuff. And then we have clock controller, and then we have pin control to control the pins for speakers and other stuff. So typical audio use cases. Let's. I think you must have already known about this. Speakers. So these are like typical digital speakers which are connected over PDM interface, and there'll be a Soundwire configuration there. So or you can use TDM as well. So and then there's an analog speakers. They are normally connected on the line out of the codec. That's typical external codec. You have an external codec wherein you're connected using MI2S or Soundwire or PCM, and then on the line out of the other side you can typically connect speakers. And then there's another use case, DMics. DMics are like digital mics, so they don't really have any analog circuits in there. It just you get digital data, so you could directly drive it into your CPU and then use it. So normally the way we connect is using the VA macro. So that's one of the thing. Headset, as I said, if you have an external codec, there we could actually connect analog audio into that. HDMI, typically the HDMI is in older SoCs, we used to have a HDMI block, and we used to also expose the HDMI interface in the LPAS system itself. Nowadays we have mostly, I think the HDMI IP block is removed and we connect using DP. So the DP interface is also available in the LPAS interfaces. So that's how we connect. External codec, I think, as I already said, could be interfaced using MI2S Slimbus or Soundwire or TDM or PCM. There's another setup of Bluetooth. So there's a codec on the Bluetooth side, which we never actually set up in our Linux, but that's something we are working on it. There's a USB offloading as well, so you could actually offload lots of USB processing onto the DSP, so the DSP will take care of it. So USB, the CPU doesn't need to do anything. So those kind of use cases are also there. Compressed offload, you're trying to play a compressed stream, then you could offload the decompression into a DSP. So those are the typical use cases. Most of these are supported upstream. Alexi, do you want to talk about your experience on RB2 and how the setup looks like?
Yeah, this is an example how components are located and how they're connected together on RB2 board. We don't have, on the left side, we have components of LPAS, digital codecs and DSP. We don't have WSA macro codec there, and components on the right, let's say external codecs, the picture can be very different on different boards. So on RB2, I2S goes into HDMI codec, or the pins are exported on low speed connector if you toggle the switches. RX macro and VA macro communicate with WCD codec via SoundWire, and WCD codec outputs analog signal into WSA amplifier, and it has speakers, and audio mic and DMic connected to WCD codec. We never tested that, and we don't know if it works. And on RB2 there is also DMic that is directly connected to VA macro and TX macro. Next one.
Yeah, thanks. Right.
Yeah. So the next things we will be talking is 3 different configurations that we have. We call them DSP bypass, where, as Srini mentioned, we program all the parts by ourselves from CPU. As far as I know, this is mostly used on Chromebooks and Google devices. So architecture.
Just want to add one more thing there. On DB410C, we have this configuration. So we bypass the DSP on DB410C, directly program the LPAS IPs.
Okay, and when audio DSP is used, we have 2 architectures. We have, let's say, old one, which is called Elite, and probably in 10 years it will be completely off. So RB2 is based on Elite, for example, RB5, RB2, RB1, and a lot of other old-ish devices. And starting with SM8450, there is new architecture called AudioReach. Basically, for me, for myself, I call Elite the architecture with static routing, and AudioReach is dynamic routing.
I think the Elite is most of the things are static. I mean, the modules are built in with the DSP, and the connections are dynamic anyway, so you could configure any module to anything. But on the AudioReach, I think the things are a bit different. I think you'll learn over the next slides. Christoph is going to talk about AudioReach in detail, but it's mostly data driven, so user can define the connections or the pipeline, how the DSP needs to process the audio. So let's talk about some of the configurations. So So this is pretty much a lot of information in one slide. What this is capturing is all the modules or all the software components involved in Qualcomm audio subsystem. So we have machine drivers at the top where it's very specific to a platform where you control pins, do a particular stuff which are specific to the platform itself, like jacks and things like that. And then we have a layer which is called a SOC layer, wherein you actually have it, which is the framework of Linux which provides the audio interface to the users. And the last layer is the Qualcomm driver. So there are three different colors of three different colors there, representing three different things. For example, the green is actually representing the drivers related to AudioReach framework, and the blue one is the Elite framework, and there's a white one which is just common across both the frameworks. And the bottom layer is the interface layer to the DSP. For example, how do you talk to the DSP? So there's a particular way to talk to it. They call it as APR or GPR, is asynchronous packet router, and the other one is generic packet router. So that's the way we communicate to the DSP using an RP message channel. So this is just representing typical setup. That's the DSP setup, and here we have a bypass setup wherein the kernel or the drivers itself program the LPass IP. So you can see there are multiple interfaces enabled. For example, the LPass I2S just enables the I2S programs I2S interface. So we have, I think we have supported 3 different interfaces. So LPass I2S also can do PCM. We have HDMI, as I said, the previous generations had this one. And the codec DMA is for TX, RX macros, which was the digital codecs in the LPass IP. So I can will go deep dive into each of them, but this is just a summary of how things look like in the software perspective. Okay, so I will be touch basing on the Elite architecture, and as I said, Christoph will take over on the AudioReach side. So Elite has, as I said to Alexia as well, it has some static services inside the DSP, which are used for configuring, endpoints. For example, you want to configure an endpoint, MI2S endpoint. There is some service called AFE, audio front end service, and then you have a data which is going to the DSP. Which is typically a PCM stream or a compressed stream, and there's a service to handle that stream that's called ASM, audio stream manager. And then in between these endpoints, for example, you have a HDMI connector there, you have a PCM data coming in here. You need to do some kind of metrics, like you want to connect one PCM stream to another endpoint. So there is something called ADM, device manager, which can actually connect different PCM streams to different endpoints, or it can mix. It has multiple topologies it can do. So those are the 3 main services which are exposed by the DSP, and based on that we actually write drivers and provide interfaces to SOC. And the DSP drivers are this. It's quite obvious that ASM drivers is stream manager, AFE is a backend front-end driver, but in PCM, in ALSA world, we call it as a PCM backend driver. So and there's also clocks which are part of LPass block, and we also have something called AFE, which can also program clocks for particular interface. So that's I try to represent a simple use case, DT. Probably most people understand the DT, how things are connected to. Let's say you want to play back on a slim buzz over to a codec, or on a headset, or on a speaker. In this case, we are trying to play on a speaker, and what we are configuring is the CPU die. It's in ALSA terminology. We configure a slim buzz, and then the ADM, the routing between the PCM streams and the codec is done by ADM, that's called Q6 routing there. And then the typical speakers, actually the WSS speakers sitting on the other end, those are configured as a codec. So that's a typical mapping there. Christoph, I think it's you.
Is it? Yeah, it's AudioReach. So
Audioreach is the new open entire framework, and last year there was a nice demo made by Qualcomm during the demo day on the Connect. You could see how in real time you could configure the DSP, you can connect the modules, you could change the use cases depending what you want, either real time, I mean like based on the laptop, or you could also predefine it differently, because it's a very extensible entire framework for managing audio on the Qualcomm devices. It's developed also open, so the SDK, libraries, all of this is they're linked here. So yeah, you can dive there later. So the architecture of the drivers and what you have in the kernel is this green boxes. So now everything which is Elite or DSP bypass is blackened out. We have the support. Let's say the Audioreach started with Qualcomm SM8450 SoC. So this was 8 plus Gen 1, I believe, by the marketing name. And we also supported the Linux kernel since, I think, 2 years. What's there? The difference comparing to the Elite is that we use a bit different transport driver, which is the GPR. The GPR talks with the DSP. All of the services here, all of the things are using the GPR packets to talk with the DSP. This is even event-driven mechanism. So you send a message, wait for reply will be coming. You also actually can receive some events from the DSP. In this entire setup, we also have a memory mapped interface for the codecs, like VA codec. And I learned today something that the VA stands for voice activation. Really cool. After some years, I can still keep learning, and it's actually proved that this is a very useful moment.
I think there is a use case for that. Typically, you can go into a very low power state, and then you want to wake up your system with voice activation. So that's the use case. So the VA subsystem is in very low power state. So you can put your system into that low power state and then say, "Hey Google," to wake it up. So that's a typical use case for VA.
Yeah. On the right side, there's an example of the graphs. I will say about graphs in a bit. So from the driver's point of view, this is a similar slide which was before. So we have the PCM front and back end. The drivers have different names. We also manage clocks. What's here different is that not APR but GPR driver for the transport, but we have also the graph data. So the graph data, we use here the audio SoC topology. So this is kind of common for the Linux kernel. Let's say the other projects like some Intel, whatever, AMD sound as well uses this topology. And we have it in a separate repository. It's on GitHub. Links are at the end of the slides. It's being compiled to the binary form. The binary form will be then stored as a firmware. This firmware comes in the Linux firmware repository, and the kernel loads it. So this topology describes the graphs. The graphs here actually consist of subgraphs, and subgraphs have different modules, and these modules represent different features for different, let's say, functions which you want to connect, like PCM decoding, PCM conversion, volume adjustment, and then it goes to some endpoint, H2RS, which would be the HDMI, or DMA endpoint. Maybe, Jenny, you have something more about the graphs? Because the next slide is as well yours, by the way.
Okay. So as I was saying, Audioreach, the framework itself is data driven. That means user has to actually tell what they want to run, and the way they tell is using the graphs. And right now what we do is we generate this graph manually. For example, in this case we are trying to play back on as Christoph was saying, on a HDMI. Then we create two graphs. One is a subgraph which is actually handling the PCM streams, another subgraph which is actually handling the hardware endpoint. The reason to do that is because you could actually multiplex or mix PCM stream into two endpoints at the same time. So that's the flexibility we get. So if you typically you could just load one graph and then just one use case works, but this actually gives you a flexibility of running one stream onto two devices or many devices, or mixing two streams into one device, or on different configuration. So that's the flexibility that gives. Currently what we have is pretty basic modules that we are working on getting interesting modules. For example, you wanted to, after volume control, you wanted to do a bass control or some kind of effects onto it. In some cases, you wanted to add some speaker protection kind of thing. So those kind of advanced modules, Christoph is also working on it. Okay, 5 minutes. Okay, yeah. So yeah, this is it. And if you have any questions, I'm happy to answer at the end of the presentation. But yeah, so do you want to talk about it? Okay, yeah. So current status is we have a SoundWire controller driver, which is pretty much heavily used on the latest platforms. That's a default audio bus on most of the Qualcomm SoCs nowadays. So what is missing in that is it only supports PDM ports right now. We are planning to add PCM support to it and SDCA support to it, which is a standard codec interface. So you don't need to actually write any codec drivers in future if the register format will be pretty much standard coming out of the specs. And there'll be some new codecs as and when the new SoC gets announced. What we have in the bypass, DSP bypass, is HDMI I2C and codec DMA support. On AudioReach, there's lots of things going on. As I was saying, speaker protection, some static calibration, control links. So these are the more graphs, and we want to generate automated graphs. So as I was saying, the graphs are written manually. We use M4 language to write the graphs. It's easy, but again, it's not automated. It's manual. So we're trying to automate some of the stuff, and we're also trying to add few more features like Opus codec and things like that. On Elite, we have most of the features working. Nothing actively development happening there, but I think Alexi is doing good job in testing some of the stuff again and fixing some of the bugs in there. Okay, what next? I think
we have a lot of things we want to look at, and there is some work in progress. We're working on speaker protection support for AudioReach. We want to look at adding more codecs and a lot of stuff in compress playback, compress offload mechanisms. We don't have a lot of UCM profiles, or all you see UCM profiles for all boards. That's also something that we need to look at. DSP drivers optimization. Yeah. It's you are looking at it, right?
Yes.
Yeah, and we will be looking at adding support for new platforms, and we'll have a lot of work in future.
Yeah. Thanks, Alex.
I think the next slide is just useful links.
Yep. I think we have got. So there's some additional effort by Qualcomm as well to open source the AudioReach framework itself. So it's available in the first link, and then we were talking about the graphs. That's part of the second link, and and we have, as I think that the third one is still again the AudioReach framework. I think it's done by Qualcomm. Yeah, that's it. Okay, if you have any questions.
I have a question.
Okay.
There is a subgraph or module in AudioReach architecture.
What was that? Sorry.
Yeah, here. Module or subgraph, is it, for example, a task in the operating system that runs on DSP?
So the concepts here, the constructs actually translate into a scheduler in the DSP. So every container is a block that gets scheduled in the DSP. So you could actually prioritize some of the containers based on your graph definition. So that is the scheduling block.
One subgraph, one container? Or it's one-to-one, or you can have several.
So you could have n number of containers in a subgraph. Subgraph is a bigger this thing, and you could have n containers in the subgraph, and each container can have n modules.
Okay. In your stack, is there anything that Qualcomm doesn't want to release, doesn't want to get upstream, like in camera and GPU? Like, are there sensitive
in audio, you mean?
Yes.
No, I don't think so. It's all public. Most of We are lagging some of the features which are available in downstream. It's because some of the features we can't test it. So.
But what should I mean, what is the recommended thing I should be running my user space? Should I use ALSA? Should I use something else? What's the least painful way to get my user space running?
Yeah, I think so. It all depends on what the environment you have. So you could, some people test command line, but typically there are sound servers available, pulse audio and Piper. Now, if you ask me which one should I use, I think the pulse audio is out of life. I think there's no active development happening there. So you should consider using Piper, and that is the default in most of the distros.
But this should also not matter because the interface to the kernel is the same. So
yeah, it's all user audio manager, right?
You have that thing Jack as well, right?
Yeah, Jack.
Pipewire, ALSA, and Jack. Is there something else?
I never used Jack, but
right.
Yeah.
Okay. Pulse audio. Right. So there's 4.
Yeah, Jack, pulse audio, and Piper, and there's.
Okay. So I think the answer was use pulse audio.
Pipewire.
It begins with a P. Okay. It's pretty close.
Yeah. I think last question. I think we are.
So in the Elite setup, the original setup, there's lots of mixers and controls and things to set up the routing and whatever.
Yeah.
Is that still there with the new AudioReach setup?
Yeah.
Right. So it's still many mixers and things, right? Okay.
Okay. Thank you all. If you have any questions, you can reach out to us, 3 of us. Thank you.